Hi students, welcome to lecture 59 in our aerospace engineering course, and today we are going to solve the orbit equation which I derived in the previous lecture. So this is the equation which is going to tell you about the orbit or the trajectory of a typical spacecraft when it is in flight around the earth. I'm Dr. Ranjan Ganguly. So let us revisit the equation which we derived in the previous class. So what we looked at was the planet Earth. This has a mass given by capital M. There is some spacecraft here at a distance given by r, and the spacecraft has a mass of small m. The angle between the horizontal line here and this line r is given by theta. So essentially we can describe the motion of this spacecraft by two coordinates, that is r and theta, and based on that we derived some equations. So essentially there was one equation, that is h is r square theta dot, which is the angular momentum per unit mass, and this is constant for a spacecraft. Also the second equation, which is the orbit equation, is r double dot minus h square by r cube plus k square by r square equal to 0, where the dot is the derivative with respect to time. K square is gm, that is a constant value. So here m is the mass of the earth, g is the gravitational constant which is there in Newton's law of gravitation, and using these numbers we can essentially find this equation, and we can have some numbers here for k square and h square. Now what we are going to do in today's lecture is we are going to solve this equation, and why this math is important is because the solution of this equation plays a big role in determining the type of orbit which this mass is going to have. So whether it is going to have a circular orbit or it is going to have a parabolic orbit is going to come out from this equation. And that is important because certain type of orbits are going to simply circle around the earth, and certain type of orbits are going to escape out of the earth. And so if you are designing a vehicle which is going to escape the earth's atmosphere, you have a certain type of orbit, and if you want something which is essentially circling around the atmosphere or the earth, you will have a certain type of orbit situation. So let's begin the solution process. So now before we even begin, you will clearly see that this is not a very simple equation, because r here is coming in the form of r cube and r square. So it's something which is somewhat complicated, and therefore in this kind of differential equation we typically use some kind of substitution or change of variables. So that is going to simplify this equation, and what we are going to do is we are going to express r as 1 by u, where u is a different variable. So we are going to define this new variable u, which is a function of r, or u is 1 by r, or we will say r is 1 by u. So this is sometime known as an auxiliary variable, because we are simply going to use this variable to solve the equation, and then we are going to revert back to r. So if r is 1 by u, we immediately get h is r square theta dot is theta dot by u square. So I essentially put r is 1 by u here, and I got this as theta dot by u square, and therefore I get an equation theta dot is h u square. So this is the equation we are going to use in some further manipulation of these quantities. So now let's try to get the first derivative of r. So r is 1 by u, theta dot is h u square from our previous slide, and now I take r dot is dr by dt. I write it as d 1 by u by dt, where I have taken r is 1 by u here. I differentiate this, so I get 1 by u square and a negative. So that I get by differentiating 1 by u from calculus, and I get the du by dt term. I write du by dt as du by d theta into d theta by dt, and then I get this equation here, because what I have done is that I have brought this theta dot here. So essentially theta dot is nothing but d theta by dt. So that theta dot has come here, and now I can use the fact that theta dot divided by u square is going to be h. Therefore theta dot by u square term becomes just h, And so I can say r dot is minus h du by d theta. So that's the equation I have written here, that r dot is minus h du by d theta. The slide before we also got theta dot is hu square. And now we are going to find the second derivative of r. Remember, the orbit equation has r double dot. Therefore, that's the second derivative we are aiming for. So we start with r double dot, and this is simply d by dt, dr by dt. So we have to differentiate with respect to time twice. So now we start substituting. So essentially we clearly see here that the first r dot or dr by dt, I can substitute minus h du by d theta, which I did here. So I get this equation. Now I take this equation, I put the minus h outside, and I write it in this manner. So essentially what I do is I bring the du by d theta, I put d by d theta, and I put d theta by dt. So essentially what would happen, this d theta would get cancelled, and this would be d by dt. So these two equations are essentially exactly same, or these two expressions are exactly same. So now I take a look at this equation and I immediately realize that this is nothing but the second derivative of u with respect to theta. So this becomes d2u by d theta 2, and this equation is here, and it further simplifies because I immediately know that d theta by dt is theta dot. So I get this equation here, and finally what I do is I substitute theta dot is hu square, and therefore I get minus h square u square d2u by d theta 2, or we can say square sometime. So essentially now I have represented r as 1 by u, I have represented r dot as minus h du by d theta, and I have represented r double dot as minus h square u square d2u by d theta 2. So let us write down these three equations here, the equation for r dot and r double dot, and then we write the orbit equation here once again. And so what we can do now is we can plug these values into the orbit equation. So we substitute for r here, we substitute for r here, and we substitute for r double dot here. So once we do that, we clearly get r double dot is this equation here. From this we get h square by r cube becomes h square into u cube, because r is 1 by u, so 1 by r would be u. Similarly for k square by r square, I get k square u square term. So this is the equation here, and I can further simplify this here. I can divide this completely by hu square and flip the negative sign. So I get d2u by d theta square plus u minus k square by h square equal to 0. So essentially that equation in red is the simpler form of this equation, which we are now going to take and work further with that. So this equation, of course, you will clearly see is in a much simpler form. It's in a form you have typically often seen even in various courses, such as in simple harmonic motion in physics and so on, or basically any kind of constant coefficient differential equation system. You have this equation here with constant coefficient, and you have a constant here which can be taken to the right hand side. So we can take this constant k square by h square to the right hand side, and we get this equation here, and we can solve this equation easily and get it in this form, where u is k square by h square plus a cos theta minus c. So of course you know that this is a equation of the second order, and therefore it would require us to have two constants. So one constant is a and the other constant is c. So that is the solution of this equation. Now we can simply check the solution. So let's start with the differential equation here. We had this u, we differentiate u with respect to theta, so this becomes 0. This becomes minus a sine theta minus c. Again differentiated with respect to theta, this becomes minus a cos theta minus c. And then I put this second derivative back here. So I get this equation here. This is the d2u by d theta 2 term. This is simply the u term here. U is k square by h square plus a cos theta minus c. That's this term here. and you have the negative k square by h square term. So there is a cancellation here, there is a cancellation here, and so you get 0. So basically this equation is the solution. So now we are not going to bother too much about u. We need to revert back to the orbit equation. So u is this, and remember that u is 1 by r. So I can immediately obtain r is 1 by u. So this is the value of u, and now I have obtained the solution r which we were interested in. So we were using u simply as an auxiliary variable to get at r. Now we have got at r and we have expressed r as a function of theta. So to summarize this important result, let's write this orbit equation clearly here. This is sometimes known as the orbit or the trajectory equation also. So this is the orbit, this is the solution r. Now this r can also be expressed in this form here. So this actually r which I have put in yellow are a function of theta is the orbit or trajectory of the spacecraft, and we see it's governed by some of the properties of the system such as h and k, and also you have constants such as a and c. So let's bring some physics back into the problem. Let's return to the earth and to the spacecraft here. You remember there was m and m here, there is theta, there is r, and so this r theta is essentially this r here as a function of theta, which is determining this motion of this mass m which is taking place in the orbit. And of course k square, if we consider earth, is given by this value. So we can essentially now find r theta because we have solved the orbit equation. So just to further cement some of these concepts, r is the orbit or trajectory of the space vehicle. R is equal to r theta. This depends on h square, a and c. Now, there are certain conditions which are often required if you want to get more out of this equation. For example, we need to get something known as the burnout condition, which will specify the path of this particular vehicle. So burnout of the rocket booster takes place at some distance, let's say r is rb from Earth center. So at some point here, there is burnout. This distance is given by rb. There is a certain velocity which this mass has here. It's given by v subscript b, and this angle is beta subscript p here. Now this angle is with respect to a line like this here, which is normal to this rb, and also this angle is theta subscript b. So this is the burnout condition. If you have this condition, it will certainly help you in getting some of the details about the solution of that equation. Now there is something interesting which comes out from analysis of this equation. We can take this orbit equation which I have put in this blue box here, and we can rewrite it in this form by declaring that p is h square by k square, that's this value here, and e is a h square by k square. So if we do that, the numerator term here h square by k square simply becomes p, and at the denominator we have 1 plus e cos theta minus c. Now, if you are familiar with mathematics of conic sections, most people study conic sections in Cartesian coordinates involving x and y. But if you know the theory in terms of polar coordinates r and theta, you will see that this is a conic section in polar coordinates, and the trajectory will depend completely on the eccentricity of the conic section, which is given here by E. So now this is a purely mathematical problem involving E, and if E is 0, the path is going to be a circle. If E is less than 1, then you have an ellipse. If E equals to 1, you will have a parabola, and if E greater than 1, the path is a hyperbola. So depending on the path, the trajectory of that flight vehicle or space vehicle is going to be different, and it is going to circle around the earth or it is going to go out of the earth's orbit. So these are conditions which are likely to take place. So essentially we can say at this point that circular and elliptical paths lead to orbit about the planet, and parabolic and hyperbolic paths result in escape from the planet. Therefore E is very important because depending on the value of E, the particular trajectory of that spacecraft is going to be there. So to summarize some of the main developments we got today, we solved the orbit equation which we derived in the previous class, and we obtained the solution in this form, and we further showed that the orbit equation solution can be written in this form here, and this is basically the equation of a conic section, and there are several conic sections out there. For example, the ellipse, the parabola, and the hyperbola. So the circle can be regarded as a special case of the elliptical section. Now we are going to study in our next lecture the different cases which are possible. So for example, we are going to take a look at the situation where you want to just revolve around the earth. So that is the case of typical satellites which you launch from the earth. These could be communication satellites, weather satellites, and so on. And in those cases, you essentially will try to stay in the elliptical orbit. And in case you want to leave the earth, you want to go somewhere else, you want to go on some interplanetary missions, you have to use the parabolic or the hyperbolic orbit. And so we are going to see the mathematics which leads to these particular outcomes, and we are going to derive the velocities which are involved here. So we are going to derive the circular velocity, and we are going to derive the escape velocity for the system. So I'll end this video here. If you have any questions, please leave them in the comment section. And if you are interested in any feedback you want to give me, again, leave it in the comment section below, and I will see you sometime soon. See you then.